So it's about drawing. You see, this is two carbon radical. How do you join them? You just put them side by side and connect them together. It sounds very simple, but when you join it, you feel a bit weird. Right? So just keep in mind, this is one of the more popular type of free radical substitution reaction they like to ask. And how do they ask you? They will ask you, which compound is formed as the trace amount? So they want to find out what is the trace product in free radical sub. And you are always looking out for one of them. And how to recognize them? The dimerization of your hydrocarbon radical. Okay, pay attention to the hydrocarbon radical dimerization, then this is the one. So this is the product that they want to draw. Now, let me move forward together to the next page. And this is the final chemistry of your arene. Now, under arene chemistry, I think I mentioned to you that arene don't go through oxidation process. Correct now. So just remain where you are. I'll show you something. In last week, what we went through, we talked about the overall view. We say that benzene don't really go through oxidation. No oxidation. And then how come I say now go through oxidation? So look very carefully here. Let's come back to here. This is not normal oxidation. This is called side chain oxidation. What is the meaning of side chain again? The side of the benzene. This is consistent to what you learn in free radical sub. So understand the word side chain is on the side of the benzene. So you're oxidizing the carbon, not the benzene. So remember, it's a carbon attached to the benzene that is being reacted. So the benzene never react. There's a difference. That's why we don't call it oxidation. You write oxidation is wrong. It's side chain oxidation reaction. Now, there is a certain pattern that you need to recognize. Think like dialing a number to a number log. If the number log got 3 digits, you type 1, 2, 3, it open. You type 1, 2, 4, can open or not? Cannot. So this is the 3 code you need to remember. The benzene must be present. The carbon must be present. The H must be present. You must have this combination present. You don't have this combination, no side chain oxidation. This combination must be there. Now, this combination is so special to the point that they even give them a name. They call it as benzylic hydrogen. This is so special. They really call it as benzylic hydrogen. Then sometimes they call the carbon atom as well, benzylic carbon, because it is so special. Okay, so keep in mind of this special name. When I say benzylic hydrogen, immediately you remember, this is the molecule we're looking about. Benzylic carbon, this is the one. Okay. Does it look like a briefcase to you? There's a briefcase and a handle. Maybe you can imagine this way, a bit more creative. Okay, but doesn't matter, let's continue. So what is the message if you see this combination coming? In the presence of KMnO4, which is the oxidizing agent, it will convert this molecule to become carboxylic acid immediately. Nobody knows the mechanism why. So it's like a black box game. They just throw it inside and they found carboxylic acid. Now, what happens if you do it instead of an acidic, you do it in an alkaline? You will form a salt. So let me give you the step-by-step process, how exactly it's being broken down. Every time when you do the alkaline condition, my recommendation is you do the acidic first, which means you will form carboxylic acid first. Think of it as acidic first. Let me write down. Now, this is done in alkaline. Now, what will happen is that in the presence of alkaline, what will happen to the OH minus? Is it capable to neutralize the acid? Oh, yes, of course. It can neutralize the acid. So you form COO minus. So this is not a simple one-step reaction. There are 2 steps. So this is what we call a 2-in-1 reaction. The first one is called side chain oxidation reaction. SCO stands for side chain oxidation. And one more reaction is called the acid-base reaction. Okay, let me write down for you the ABR abbreviation. ABR abbreviation is called acid-base reaction. Okay, so there are 2 reactions in one. It's not one reaction. Okay? 2 reactions in one reagent. Now, as you are transiting right to the next level of organic, Gradually in J2, you will learn 1 reagent, maximum can do 10 reactions. Now we do 1 by 1. Now it's like 2 in 1 right now. Then gradually we'll level up to 3 to 4 to 5 to 6. Now let's take a look at some examples together so you will clearly understand how it's being applied. So for example, the first one. The first one, we're talking about the side chain oxidation of your methyl benzene. Now, I like to re-represent my methyl benzene a bit. So it's correct, I just re-represent it. I want to re-represent it so it's clearer for our observation. Now, do you notice it? This is a what? Benzylic hydrogen. So I need you to train your eyes to see it. It's all about training your eyes to see it. Once you see it, it's yours already. Benzylic hydrogen undergo oxidation, it becomes carboxylic acid. What happened to these two H? H2O. Now, what happens if you have a carbon with a benzene but no H? Well, just like the example I give it to you, the number code is 1, 2, 3. You dial in 1, 2, 4. Can open the lock? Cannot. This one got 1, 2, not the 3. So therefore, the lock do not open. Hence, no reaction. The combination is very fixed. You only can have a benzene, a C, and a H. No such combination, too bad, no reaction at all. And let me give you a little bit more complicated example. Let's take a look at the example below. So this is a CH2, CH3. Do you